Okay, so in this chapter, we'll study fixed axis rotation. Okay, so for instance, what this means is, so here's an object. So this, what we'll be doing is studying rotational motion of a rigid object. A rigid object meaning not a cup of coffee. So this guy is rotating about this axis. Okay, so it's rotating like that. That's what we mean by fixed axis rotation. Now, so this seems quite different than anything that we've seen. Okay, but so let me remind you of motion in 1D. Okay, so we initially started off by seeing motion in one dimension, meaning an object that would travel along this straight line, and we call this the x-axis. Okay, and so let's say if you wanted to describe this motion, how would you describe this motion? Do you guys remember? If you wanted to describe any motion in one dimension, what is it that we're asking you for? What we're asking you for is x as a function of time. Remember? And given x as a function of time, you could calculate the velocity, which was dx by dt, and you could calculate its acceleration, which was d square x by dt square, and so on. Okay. And another thing that you noted was in one-dimensional motion, vectors could only point in one of two ways. And so, to represent the direction of the vector, we just used the sign. Okay, so the sign told you which way the vector was pointing. Okay, so this was one-dimensional motion. Now it turns out that, you might not realize, it's not too obvious, but these rotational motion about a fixed axis and this one-dimensional motion are cousins. Okay. So every formula that you've seen for this motion will give you a corresponding formula for this motion. Okay. So again, I'm recording this, but so these guys won't be able to see this. So here's an object. This is the axis of rotation, so I'm spinning this bicycle wheel. So there's the axis of rotation, and this thing is rotating on that. Okay. So what we'll do is we will measure its position. So that's the x-axis, and let's say we mark this point over here on the wheel, and we'll measure the position of this wheel with respect to that x-axis. Okay. What is the position of that point with respect to the x-axis right now? 90 degrees. Okay. What is the position of this guy now with respect to the x-axis? 180 degrees. Okay. Through what angle did this point rotate through? It was initially at 90 degrees. Now it's at 180 degrees. What angle did this rotate to? 90 degrees. What angle did this point rotate to? What angle did this point rotate to? 90 degrees. Okay. So you see every point on that object rotated through 90 degrees. Okay. All right, let's go back to this guy. When we were talking about this big car, okay, let's say this car went from here to there. It traveled 10 meters. What distance did this point travel? I'm sorry? 10 meters. How about this guy? 10 meters. Every point rotated through 10 meters. Just like that, in that object, in that spinning wheel, okay, this was your reference axis, and when this point rotates through an angle of 30 degrees, every point rotates through an angle of 30 degrees, okay? So we will describe the position of this object. You'll just draw a line on the object, okay? And this will be the position of this object, okay? And it's rotating about an axis that's perpendicular to its plane, okay? And so if it's spinning, to describe that motion, what is it that you will want? You will want its angular position as a function of time. This will be a description of motion, okay? And just like you had, this was description of motion in one dimension. This is a description of motion of rotation about a fixed axis. Okay. What was this? We defined a velocity as a function of time, velocity of the object, which was dx by dt. Similarly, we'll define angular velocity, denoted by omega, which will be d theta by dt. Okay. We defined linear acceleration, which was equal to dv by dt, which was d square x by dt square. We'll similarly define angular acceleration, denoted by alpha, d omega by dt, which will okay, so if A was constant, then you guys remember V final velocity, this is in 1D, okay, was equal to V naught plus AT. V square was equal to V naught square plus 2AX minus X naught. And X minus X naught was equal to V naught T plus 1/2 AT squared. Right, so you'll get an exactly analog, you'll get very similar formula when alpha, angular acceleration, is constant. Final omega, angular velocity, is initial angular velocity plus alpha times t. Okay. Final angular velocity is initial angular velocity square plus 2 alpha times theta final minus theta initial. This is the angular displacement. Okay. And theta minus theta naught. Okay, so the angular displacement will be omega naught t plus 1/2 alpha t squared. All right, so what we are saying is this motion in one dimension and rotation about a fixed axis for a rigid object, these guys are cousins, even though they look so different. Okay? And so for every formula that we've derived for this guy, we'll derive for this guy. So what you've learned in the first 9 chapters, you will learn in the next 2 chapters for rotational motion. Okay, so that's what we're going to do. All right, so rotational variable, you saw angular position will describe the position of the object, will define angular velocity and acceleration. Okay. By the way, this is a centrifuge. This is in Houston, I believe. Okay. And what you can do with this thing is, in which astronauts can be subjected to 20 Gs. Okay, so what they do is, so they spin this fast, okay, and what you can do is you can put an astronaut here um, with their head like that. They're laying down there. What does this do? Okay, so we are on Earth here. We are on Earth here. You're standing here. There's your heart, and you know you got to send blood to your brains, otherwise you'll pass out. So the heart has to pump the blood up that high. Okay. Now this is against G. What if you increase gravity? What would happen? I'm sorry? It's got to work harder. All right? So that's what this device does. It increases gravity to 20 Gs when you put them and spin. Effectively, it's 20 Gs in this direction, so your heart is having to work harder. Okay? And if you experience that kind of Gs, how long does it take you to pass out? Yeah. And so fighter pilots and all learn to tighten their muscles and all that, so blood doesn't flow while they're going into a dive. Okay, and that's what pressurized suits are about. Anyway, okay, so a guy like me probably would pass out in 30 seconds or something like that. Yeah. All right, so you see many rotating objects. So here's an object that's rotating about that fixed axis. Okay, this is a rigid object, so if this guy rotates to 30 degrees, this guy will rotate. Every point on that object will rotate through 30 degrees. Okay, so to describe the motion of that guy, all you have to do is give the angular position as a function of time. Okay, this is describing motion. So this is describing the rotational motion of the object. Okay. So for a rigid object rotating about a fixed axis, okay, all parts of the object rotate through the same angle, and we are going to use this to describe the motion. Okay. So for instance, here's a disk that is rotating, so just like for this object moving, the convention was when it moves to the right, those are positive directions, and when it moves to the left, it's negative directions. Just like that, for rotating objects, counterclockwise rotations are taken positive, and clockwise rotations are taken negative angles. Okay? So, and just like you're measuring distances relative to an origin, we'll measure angles relative to a reference line. Again, we'll call that the x-axis or whatever you want to call it. So this is the reference line, and we'll measure its angular position with reference to that. Okay. So when this point, which is a distance r from the axis, when this point travels distance s, the angle through which this object has rotated is theta, is given by that. It's s over r. Okay. And theta is in radians. Okay, so there's that disk. Imagine that disk. There was the initial angular position of the disk, and then it rotated some more. There's the final angular position. So the angular displacement is the final angular position minus the initial angular position. Okay. And this is the parallel of this equation, x final minus x initial. Okay. So when an object was x initial, this was the angular displacement. Okay. So the parallel of this linear motion is this angular displacement. Okay, so if you wanted to describe this position, you're giving this as a function of time, remember? Theta as a function of time. Okay. So this would be at t final, this would be at t initial. We had defined average velocity as displacement divided by time. So just like that, angular velocity, okay, now this says angular speed will give you the direction in a second. Angular velocity, average angular velocity is displacement over time. Okay, this is omega. But what we are really interested in is in the limit delta t going to 0. Okay, so the instantaneous angular velocity is given by d theta by dt. Okay. Omega is d theta by dt. Okay, so what is the direction of the velocity? So for one-dimensional motion, the velocity was either in that direction or that direction. Okay, so here's the convention for the direction of the velocity. So if an object is spinning like this, use your right hand. If your fingers point in the direction of the rotation, your thumb points in the direction of the velocity. Okay, so the velocity points along the axes. Okay, so it can either point this way or that way. And counterclockwise rotations are taken to be positive. Clockwise rotations are taken to be negative. Okay. Okay. Notice here's now one thing you have to be careful about is the following. So this rotation looking at from here, it looks counterclockwise. And the same rotation looking from here would appear clockwise. Okay, so you have to agree to where you're looking from. Okay, you have to specify that. All right, so again, velocity vectors point along the axis. So there's the velocity vector. This is positive and this is negative velocity. Okay. When do you have acceleration? You have acceleration when the velocity changes. So we're talking about angular acceleration. Angular acceleration is denoted by alpha. And when angular velocity changes, then you have acceleration. Okay? So angular acceleration is d omega by dt, time derivative of that. All right, so let's do an example. So let's say this object is rotating and we are measuring its angular position with reference to some line. Okay, so let's say this is the line with reference to which we are measuring theta t. Okay, so let me give you an example of a motion. So theta t is, let's say, 7t cubed plus 5t squared plus 4t plus 10. Okay, so let's say that's the angular position of that object as a function of time. Its angular velocity as a function of time is d theta by dt, which is 21t squared plus 10t plus 4. Its angular acceleration would be (42t plus 10). Okay, this would be radians per second and radians per second squared. Those would be the units. Okay. So just like what you learned in the previous chapters, so you're doing the same thing for rotational motion. Okay. So again, very surprising. It seems like this motion, you would not guess that this motion and this motion are cousins, but they are. Okay. So all the same equations would apply. So for every equation you have there, we'll get a corresponding equation for rotational motion. Okay. All right, now in all these equations, as this object rotates, okay, so let's say it starts here, What is the angle through which it has rotated? 360. Now 720. Okay, 1080 and so on. So you don't reset at 360 degrees. So in all these equations, okay, the angle keeps increasing. All right. So let's say here's the initial velocity. When the speed of the object is increasing, the acceleration is pointing in the same direction. Okay. And when the speed of the object is decreasing, the acceleration is pointing in the opposite direction. Okay. So just like that, for rotational motion, if the angular speed is increasing, the acceleration is pointing in the same direction as angular velocity. And if angular speed is decreasing, the angular acceleration is pointing in the opposite direction. Okay? So let me illustrate this. Okay, so we'll do this on the bicycle wheel here. So which way is the angular velocity pointing? You point your fingers in the direction of rotation, and that's, you gotta use your right hand, okay, that's the velocity. Okay. Now, acceleration, it's accelerating, acceleration is pointing in the same direction as velocity. Now it's decelerating, so acceleration was pointing in the opposite direction of the velocity. Okay. All right. Now, so here we won't use this in problems, but I just want to mention this. So displacement, okay, so theta, delta theta, theta minus theta initial, okay, this is a vector, okay, and so the question is, what is the direction of that vector? Okay, now this formula works for infinitesimal displacements, okay. So let's say if this object rotated through d theta, okay, so this was the initial position of that point, and there's the final position, and that was d theta. Okay, so when this point moved from here to there, the object rotated through an angle d theta, okay, and this would be d theta. Okay, so d theta is, this is the magnitude of the angle, and the direction is in this direction. Okay, so what this is telling you is the distance that this vector, this point moved. Okay, ds. Okay, so let me draw a new diagram. Okay, so the vector d theta is pointing in that direction, r, and this distance is ds. So ds, the displacement, linear displacement of this point is d theta, this vector, d theta, which is the magnitude of that angle, cross r. R is the initial position of the point, position vector of the point, okay? So there's the vector nature of that displacement, okay? So the vector, again, all the vectors point along the axis of rotation, okay? And so if the object is rotating this way, the displacement vector is pointing in that direction. Okay. Again, we won't worry about that too much. And what this is showing you is so as this object rotates, the velocity of this point, the instantaneous velocity of that point is given by angular velocity of that object cross with r. R is the position vector of that point with respect to the axis of rotation. Okay. So the linear velocity of that point is equal to angular velocity of the rotating object. So again, there's the object that's rotating about that axis. Okay. And omega is the angular velocity of that object cross r gives you the linear velocity of this. Okay, so again, if this was a disk and it had angular acceleration, again, all displacement, velocity, and acceleration point along the axis. If this guy had angular acceleration, what that means is it's spinning faster and faster. Okay, that's when you have angular acceleration. If it's spinning faster and faster, then the speed of this guy is increasing. Each point is going in a circle, and the tangential acceleration of that guy is given by alpha times r. Okay, alpha cross r. And of course, it'll have a centripetal acceleration as well, but the tangential acceleration is given by that. Okay. This point will have a centripetal acceleration because the velocity is changing direction. This guy is related to the magnitude of the rate of change of the magnitude of the velocity. Okay. Okay, now we'll give you the kinematic equations. So here's an object, and let's say we are measuring its angular position with reference to some axis. Okay. So this guy is rotating, and what we'll be looking at, so we'll study this motion. We'll give you equations when the acceleration is constant. Okay. So again, angular acceleration is given by d omega by dt. Okay. And again, so you can integrate both sides of the equation. So alpha dt. Okay, so what we're going to do is derive this equation, the parallel of this equation. Okay. So this equation for one-dimensional motion was, this gives you final velocity in terms of initial velocity and acceleration. So final velocity was initial velocity plus acceleration times time. Okay, so this gave you velocity as a function of time. So we're going to do the same thing for rotational motion. Alpha dt equal to d omega by dt from 0 to t, t initial to t final, let's say. Okay, if for constant, when alpha is constant, this comes out. Okay, so this will be alpha times t final minus t initial. And this will be using the fundamental theorem of calculus. This is the integration is the antiderivative, so this will be omega final minus omega initial. Okay, so omega, and we'll call this t. Omega final minus, well, alpha times t. Omega final is omega initial plus alpha times t. Okay, so this is exactly similar to that equation. Okay. Similarly, you can do this with position as well. So omega is dt theta by dt. So you can integrate both sides, and what you get is theta as a function of time. Okay, so you can get that. And similarly, you can get, you can derive angular displacement, final angular velocity is equal to, square is equal to initial angular velocity squared plus 2 alpha times theta final minus theta initial. Okay. So again, what we're saying is the following. So these are the kinematic equations for rotational and linear motion under constant acceleration. So when this is when alpha is constant, and this is when this is linear motion, this is when linear acceleration is constant. When A is constant, V final is equal to V initial plus A times T. Similarly, omega final is equal to omega initial plus alpha times T. So every equation that you've seen here, okay, so if you do the following replacement, if you replace x by theta, v by omega, and a by alpha, you can go from here to there. Okay, so with this replacement, every equation you had for linear motion, you get the corresponding equation for angular motion. Okay. So like I said, those motions are related, and so you get the same equations. Okay. Now we'll derive some of the other equations that you've seen for linear motion. Okay. All right, so when this object is rotating, so it's rotating about that axis coming out of the plane. Okay, this object is rotating. Okay, so for this point, see the velocity vector is changing, so this point in a little while will be here. And so this has centripetal acceleration. Okay. But this linear speed of this point, okay, the linear speed, okay, so the further out this point is, okay, so if you're looking at this point, okay, so this point is traveling faster. Okay, so the further out you are from the axis of rotation, the faster you're moving. The speed of this guy is given by the speed of that point is given by how far you're from the axis times the rotational speed of this object. Okay, so what this formula is doing is relating the linear speed of this guy to the rotational speed of the object. Okay. Now, whenever you have these formulas that are relating linear speed and angular speeds, the angular speed, this has to be in radians per second. Okay, so the units of that are radians per second. So this is in meters per second, that's in meters, and that's radians per second. And if this is in feet, that would be feet per second, and so on. But the angular speed has to be in radians per second. So that's what this formula is doing. Okay, it's giving you the linear speed in terms of the angular speed of this object. Yeah. Now, if this guy is accelerating, he will have a tangential acceleration. This point will have a tangential acceleration, and he'll also have a centripetal acceleration because the direction of the velocity is changing. Okay. So the tangential acceleration is related to the angular acceleration. Okay, so the tangential acceleration of that point, the rate at which his speed is changing is r alpha. And again, here is a linear quantity being associated with angular quantity, and this has to be, alpha has to be in radians per second squared. Okay. The centripetal acceleration is related to the instantaneous angular velocity. Okay, what is the angular velocity of this object at this instant? And so the centripetal acceleration is r omega squared. Okay. And the further out you are, greater your centripetal acceleration. All right, so when this guy is accelerating, the linear speed is changing, so you have tangential acceleration, and since the velocity of the guy is changing, the direction of the velocity is changing, you have centripetal acceleration, which is that r square, r omega square. Okay. Whenever any object moves, okay, it has a kinetic energy. Now, when this object moved in a straight line, every point was moving with the same velocity, and the kinetic energy was 1/2 mv squared. Okay, the entire mass. Now, when this guy is rotating, it has kinetic energy too, except that all points are moving at different velocity. This guy is moving at a smaller velocity than that guy. For a given distance from the axis of rotation, you have the same velocity, but for these guys have different velocities. So how do you get the kinetic energy of this? Okay, well, you use your calculus knowledge. Okay, you break it up into little pieces. The kinetic energy of this whole thing is the kinetic energy of this piece plus the kinetic energy of this piece, and so on. That's what's written here. It's the kinetic energy of each little piece times velocity squared. Now, the velocity of each little piece is how far you are from the axis of rotation times omega, which is the angular velocity. Now, the angular velocity is the same for every piece. It is omega squared. Is r omega. So if you square that, omega is the same, that comes out, half is the same, that's a common factor. So what you get is this factor. That's the mass of each little piece times the distance of that piece from the axis of rotation. Okay, square. Okay, and that is summed over all the little pieces. So we'll give this guy a new name. We'll call it the moment of inertia. Okay. So the moment of inertia is the mass of each little piece times the distance of that piece from the axis of rotation squared. Okay. Now, so the moment of inertia of this object about that axis is this guy. And so now the kinetic energy of rotation is 1/2 I omega squared. So this formula is very similar to that. So you see moment of inertia is playing the role of mass. Remember, velocity got replaced by angular velocity. So here's a very similar formula. Here's the difference. The mass of this guy doesn't change, but the moment of inertia of a given object can have infinite values. See, the moment of inertia of this object about this axis is different than this axis, is different than that axis, then, okay. So the moment of inertia depends on the axis, choice of axis, because these r distances will change. Okay, so while the mass of an object is the same, the moment of inertia of that same object depends on the choice of axes. Okay. And it's got an infinite number of values. Okay, so for instance, so here's for a discrete object. Let's say you calculate the moment of inertia of this object about this axis. Okay. So if you're spinning it about this axis, the moment of inertia would be, see, these guys are right on the axis, so they contribute 0. And the moment of inertia of this guy will be ma squared plus, okay. So it's 2ma squared. For the same object, if you were rotating about this axis, the moment of inertia is, for this guy, ma squared plus ma squared plus mb squared plus mb squared. So the moment of inertia is that. Okay. So if you were rotating about this axis coming out of the paper with an angular velocity of 5 radians per second, And if you were rotating about this axis at 5 radians per second, for the same angular velocity, since this moment of inertia was greater, you have greater kinetic energy here. Okay? So what we are saying is, so in this case, so here's an illustration of that. So for this angular velocity, this has a kinetic energy. And for the same wheel, if you rotate it about this axis, with the same angular speed, this guy will have greater kinetic. Because the moment of inertia here, but this axis was greater than the moment of inertia by this axis. So again, the moment of inertia of an object is the parallel of its mass, except that an object has only one mass. It has an infinite number of moments of inertia, depending on what axis you calculate it. Calculate the moment of inertia by. Yeah. So here is the formula for the moment of inertia, I guess. So the formula for the moment of inertia for a discrete mass distribution is this. Okay. So we will generalize this for a continuous distribution. We'll replace this by dm. Okay. So r squared dm, and then you integrate. Okay. And if the object has uniform density, dm, the mass of a little volume is given by the density times the little volume. Okay. And that's what this formula is. So the moment of inertia is rho r squared dv. And that, so this is a triple integral. Okay. So if you wanted to calculate the moment of inertia of a continuous distribution, you would have to do this triple integral. Yeah. So in Cartesian coordinates, you would write this as dx, dy, dz. Okay, of course, if it was a cylindrical object, what you want to use is cylindrical polar coordinates and so on. Yeah. All right, now these guys are important enough where they have done these integrals for you. Okay, and so here's a table of moment of inertia. Yeah. So they've done those integrals about very special axes. Okay, so for a ring, they've done that integral about that axis. For a cylindrical object, they've done that integral about that axis, and there's the moment of inertia. For a solid sphere, they've done that integral about that axis. Again, you have to be smart about the choice of coordinate system you use. Okay. So for this axis, you will have to use spherical polar coordinates. For this guy's cylindrical polar coordinates, and so on. Okay, to do that triple integral. But again, people are not nice, and they've done this integral, and they give you this table. Yep.
So all the questions have to be with these specific ones?
All right, very good. Okay, how many different moments of inertia can this guy have? Infinite, depending on what axis it is calculating. So our friend just asked that question. Well, they gave you one value out of infinite values. What if I want to calculate the moment of inertia of this guy around that axis? Around that axis. That's where this parallel axis theorem comes in. All right, so what this theorem says is, if you know the moment of inertia of this object about this axis, okay, so that's where the standard tables will give you the moment of inertia about that axis. To find the moment of inertia of that same object about a parallel axis is very easy. It's the moment of inertia about this axis times the mass of this object times this distance squared. That's what this is telling you. The moment of inertia about this axis is the moment of inertia about this axis time plus the mass of the object times d squared. Okay. All right, so using this theorem, you guys understand, you can calculate the moment of inertia of this object about this axis, but you can't calculate the moment of inertia of this object about that axis. Okay? You can only calculate it about a parallel axis. Okay? But still, you're one step ahead. Okay? All right. All right, so let's say in linear motion, there was the velocity of this object. Now, what if I wanted to change the motion of that object, meaning I wanted to change its velocity? What would I have to do? What do I have to do?
Apply a force.
You apply a force. So to change the motion, meaning give it acceleration, you have to apply a force. Okay? Now, if this object is rotating, that's its initial angular velocity. If I want to change its velocity, angular velocity, what I have to do is apply a torque. Okay? So the parallel of force is a torque in angular motion. Okay? And so here's a torque. Okay, so let me come here. Okay. So what is its angular velocity right now? 0. I apply a force and change its angular velocity. Now if I apply the same force, is the effect the same? Okay, so here's where you might have experienced this. Let's say you're loosening a nut. You have a wrench, this wrench, and you apply force, and this thing did open. And you have a longer wrench, and you apply the same force, and the nut open. You apply the same force, but why did it open? Why did it open? So the effectiveness of a force in causing rotational motion depends on the magnitude of the force, and it depends on this distance, which is called the moment arm. All right, so the parallel of forces, a torque. The torque depends on both the force and the moment arm. Okay, forces can cause linear motion and rotational motion. Okay, so this force, if you apply this force, okay, right now, let's say this force is not there. This object can rotate about that axis. If you apply this force, this object will rotate counterclockwise. If you apply the same force here, the effect would be less. It would have a smaller acceleration. What if you applied the force here on the axis? Would the object rotate? No. So for instance, that's why they don't put these door handles on the hinge. If you put the door handle on the hinge, you're never going to go through it. That's why they put the door handle on this edge of the door. If they put it there, it will work twice as hard. All right. So the efficacy of a force in causing rotational motion depends on its moment arm. This is the moment arm. The moment arm is perpendicular distance from the line of action of the force to the axis of rotation, or to the point about which you're calculating the torque. Okay? The product of the force and the moment arm is called the torque. So torque is equal to force times the moment arm. That's how it's written. Okay? So when you get a hold of a longer wrench, what you're doing is you're increasing R. Okay? And you're getting a greater torque, and that's how it's more effective. Okay? So for instance, uh, the torque of this force is this force times this moment arm. Okay? So the torque tau is equal to force times moment arm. Okay, so if you want to increase torque, you can either increase the applied force or increase the moment arm. Okay, so for instance, in these two cases, the forces are the same, but here the moment arm is greater, the torque is greater. Okay, moment arm is smaller, torque is smaller. Okay, and in this case, again here, so if you apply a force in this direction, okay, there's the moment arm, okay, and that's a small moment arm, and the torque will be less for this guy. Okay. All right, so forces cause linear motion and angular motion. Okay, so and the effect of a force in causing angular motion depends on the moment arm. Okay, and what you'll see, okay, I'm going to stop here because there are too many slides. So just like, what was Newton's second law? I'm sorry? Force equals mass times acceleration. When was this good? I'm sorry? No. When mass does not change. It was not good for Elon Musk's vehicles. Okay. So similarly, we'll get an equation torque as mass is replaced by moment of inertia, alpha. Okay, what was the general form of Newton's second law? Anybody? When is it always valid? Even for Elon Musk? dP by dt, right? So this will be when the moment of inertia does not change, and when the moment of inertia changes, torque will be given by dL by dt. Okay, so the parallel of linear momentum will be angular momentum, and this will be your general form of Newton's second law. Okay, and we'll talk about all of this, I guess, next Wednesday.